In today's video, we're going to look at section 1.2, which is the slope of a straight line. So for any non-vertical line, any line that is not of the form x is equal to some constant a, like we looked at in the last video, we should be able to write it in slope-intercept form. So slope-intercept form of the equation of a line is always y is equal to mx plus b, where m and b are constants. So that is always the slope-intercept form of a particular equation of a line. Reason that we can't put a vertical line in this particular form is because a vertical line is of the form x is equal to a. You cannot rearrange that to have the form y is equal to something in x plus a constant, okay? That doesn't work. You can have a horizontal line in this form. It would just mean that m is 0. Therefore, the x term would go away and you would have a y is equal to a constant. But any line of the form x is equal to a, where a is a constant, cannot be written in this form. So for any line where x is equal to a, where a is a constant, cannot be written in this form. So any vertical line cannot be written in that form. Why is this called the slope-intercept form? M, this particular constant here, m, is called the slope of a line. That tells you how steep the line is. So m is just a measurement of the steepness of a graph. So m is the slope of the line. So it tells you how steep that particular line is. This particular term here, b, that constant, that is actually the y-coordinate of the y-intercept. If you go back to our previous examples in the last video, you will actually notice that pattern occurring. Whenever we had a line that was in slope-intercept form and then we found the y-intercept for that line, you will always notice that that constant b turned out to be the y-coordinate of that y-intercept. So b here is just the y-coordinate of the y-intercept. So remember, the y-intercept always has 0 as its x component, as its x-coordinate, and then that value b, that constant, would be the y-coordinate of that y-intercept. So that is why it's called the slope-intercept form. M is just a measure, it's the slope, it's a measure of the steepness of the graph. The higher the magnitude, whether it be positive or negative, the higher the magnitude of m, the steeper the graph. The smaller the value of m, or the lower the magnitude, I should say, so the closer it is to 0, that means that that line is going to be more and more horizontal. Okay? It will go towards a horizontal line as m approaches 0. For b, it's always going to be the y-coordinate of that y-intercept. So when we talked about x is equal to a, because that is a vertical line, we actually say that the slope is undefined for that line because it cannot be written in slope-intercept form. We cannot find a value for m, we cannot measure its steepness. Therefore, we say that x is equal to a has no, it's not that it doesn't have a slope, it's that that slope is undefined. So it has an undefined slope. Okay. Let's do some quick examples. So for y is equal to 2x minus 1, what is the slope of this particular line? M would be 2. If we wanted to find the y-intercept, the y-intercept always has 0 as its x-coordinate, and then its y-coordinate would be the value of b, which in this case is -1. For y is equal to 2, okay, we have no x component to this particular equation, okay? We don't have m times x because m is 0, okay? M is 0 in this case, so it has a 0 slope. That means that this line is actually going to be horizontal, which makes sense when we looked at equations of this form, when we graphed their line. Anything of the form y is equal to some constant was always going to be a flat line. It's going to be a horizontal line. What is the y-intercept? Okay, y-intercept, as we said, always has a 0 x-coordinate, and its y-coordinate is going to be whatever that b value is, whatever that constant is, which in this case is 2. So that again agreed with when we graphed this equation before, that agrees with the y-intercept. Now we have, let's try 2y plus 10x is equal to 1. Okay. I want to find the slope and the y-intercept. Now this line is in the general form for the equation of a line. It's not in slope-intercept form, so we've got to rearrange it in order to read off what the slope and the y-intercept would be. So to do that, I'm going to subtract 10x from both sides. I'm going to get my x on one side, on that right-hand side. I'm going to keep my y on the left-hand side. So if I subtract 10x from both sides, that will keep my y on the left-hand side and will put my x term on the right-hand side. And then if I divide both sides through by 2, that leaves me with y is equal to negative 5x plus 1/2. Again, remember to divide 2 into every single term that is on that right-hand side. Now I'm in slope-intercept form. I have y is equal to some constant m times x plus a constant b. Okay, so I can read off that my slope is negative 5, and then my y-intercept of this line is going to have 0 for its x-coordinate and 1/2 for its y-coordinate. This is great if we are given the actual equation of the line. No matter what form that equation is in, we can always put it into slope-intercept form and find that slope. It's very easy to do. But what happens if we aren't given the equation of the line, but instead we are just given a couple points that lie on the line? And they say to you, okay, if these 2 points lie on the line, give me the slope of the line. How do I do it? Okay. That is actually something called the alternative definition of a slope. It's just a different way to find the slope given some different information. So alternative definition of a slope. So if we, instead of being given the equation of the line and finding the slope, this time we are going to be given 2 points on the line. So if we are given 2 points, I'm going to call them x sub 1 and y sub 1 and x sub 2 and y sub 2. Okay, so we've got 2 points that lie on that line. Okay.
The important thing here is that x1 and x2 should not be equal. If that were the case, that would mean that for a given x coordinate, there were 2 separate y coordinates for that one x coordinate. That would mean that you actually had a vertical line, because that is the only time that happens with a straight line, if you've got there are separate y coordinates for one given x coordinate. So a big thing to remember here is that x1 and x2 cannot be the same. It also does not work for our formula. So for 2 separate points, x1, y1 and x2, y2 on a line where x sub 1 and x sub 2 are not equal, then you can find the slope of the line. Again, we're going to call that slope m, and it's going to be y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. You can see from this formula why it wouldn't work if both of those x coordinates were the same, because then x sub 2 minus x sub 1 would be 0. You would be dividing by 0, which obviously isn't allowed in mathematics. So remember here that x1 and x2 cannot equal one another, but we can still find the slope of a line just given 2 points on that line. Okay? We don't necessarily need the whole equation of the line, we just need 2 points on the line. So this gives us another way of finding the slope. The first way we found the slope was if we were given the actual equation of the line, we could pull it out from making the equation of the line into slope-intercept form. We could just pull out that value of m. Or if we don't have the equation of the line, but we do have 2 points that lie on the line, we can immediately pull out what the slope is by using this formula. Let's try an example where we can do this. Okay, so we're going to find the slope of the line that goes through the points 1, 4 and 3, 7. Now we have to label our points x sub 1, y sub 1 and x sub 2 and y sub 2. It doesn't matter which way around you label the points, just make sure that you stay consistent. So whichever point has sub 1, keep that the same. Whichever point has sub 2, keep that the same, because otherwise you will actually end up with a weird answer when you go to find the slope. So it doesn't matter which way around you want to label these points. I'll just go with the order that they're in. So I'll call x sub 1, y sub 1, that first point that we had, and x sub 2, y sub 2, that second point that we had. Okay. Now remember which way around you put these. So we're going to do y2 minus y1 divided by x2, so that x coordinate, minus this x coordinate. So make sure you get them the right way around, because otherwise you will end up with a weird answer at the end. So m, we said our slope was y2 minus y1 over x2 minus x sub 1. Okay. So y sub 2 we said was 7 and y sub 1 was 4. So our numerator for this fraction is 7 minus 4. And our denominator would be x sub 2, which is 3, minus x sub 1, which is 1. So it would be 3 minus 1. So our numerator would be 3, our denominator would be 2. Okay. It doesn't matter which way around you have chosen your points, so whichever coordinates you have picked. So I could have said that x sub 1, y sub 1 was 3, 7, and x sub 2, y sub 2 would have been 1, 4. That's fine. You will just end up with, if you would have done that, you would have had negative 3 divided by negative 2. The negatives would have cancelled out and you would still end up with 3 over 2. Okay, so it really doesn't matter which way around that you would have put this. I'm going to do a very quick bit of algebra here to show you why this formula actually works if you are interested. Okay, so this formula that we have suddenly come up with for m to find the slope if you're just given 2 random points, why does it work? I'm just going to do a very quick bit of algebra here to show you if you are interested. Let's say that you have a formula y equals mx plus b, okay, for some line. Okay. If you pick 2 random points on that line, so we'll pick our 2 random points, x1, y1, and x2, y2. So they're 2 random points that lie on this random line, y is equal to mx plus b. If those 2 points land on that line, it means that they must satisfy the equation. So I can plug them in, and the left and the right hand sides must be equal. So they must satisfy the equation, and this occurs for both points because they both land on the line. So I know that that is the case because both those points satisfy that line. Okay. What I'm going to do, and this seems kind of a strange thing to do, but we're going to go with it. If I do y2 minus y1, what's another way of writing that? Well, I can do my y2 term, which was mx2 plus b, minus what I had for y1. Okay. I'm going to rearrange this, okay, and actually draw out that negative. So I would have mx sub 2 plus b minus mx sub 1, but I've got to actually put that negative in front of both the mx sub 1 and the b. So I've got to multiply it out. So I would have minus mx sub 1 minus b. Okay. I'm going to rearrange this and put all of my x terms together, so all of my x sub 2's and x sub 1's, and then draw out the m and put the b's together. So I can also write this like this. To start with, I've got plus b minus b. So that's actually going to cancel out, okay, to 0, which leaves me with m multiplied by x2 minus x1. To find m, I can divide through by x2 minus x1 on both sides. So if I divide my left-hand side by x2 minus x1, and I divide my right-hand side by x2 minus x1, on my left-hand side, I would have y2 minus y1 over x2 minus x1, and on my right-hand side, I would just have m, because x2 minus x1 would cancel on both the numerator and the denominator. That tells me that my slope is equal to y2 minus y1 over x2 minus x1. Okay? So that's how this formula can arise. So if I've got an equation for a line and I've got two separate points that both satisfy that equation, so they both land on the line, I can plug those points in, and then just by doing some manipulation, I can find out a value for m.
The next thing I want to look at is the steepness property of a line. So we're going to define this. This is going to give us another case where we can use that slope value m. So let's say that a particular line has slope m. So you have a particular line, you found the equation of the line, and that line has a particular slope m. If I start at any point on the line, if I move 1 unit to the right, in order to still land on the line and get to the next point a unit over on the line, I have to go m units either up or down, depending on whether the slope is positive or negative, so whether my value of m is positive or negative. We'll write that down, and then I'll draw some examples so that you can kind of see what I'm talking about. So starting at any point on the line, if we move 1 unit to the right, which means that we are moving 1 unit in the positive x direction. So if we started at a particular point on the line where x was equal to 2, for instance, we would be moving over to where x is equal to 3. We are moving 1 unit over to the right. So if we move 1 unit to the right, we must move m units either up or down. So m units vertically, depending on whether m is positive or negative, depends on whether you'll move up or down, in order to be back on that line. Okay. So as I said, if m is positive, you move up. If m is negative, you move down. Why is that? If I do a quick sketch here, okay, you will always find that a line with positive slope will rise as you go from left to right. So a line with positive slope will look something like that. For instance, this is just a random sketch of a line. But that line will have positive slope. It rises as you go from left to right on the graph. Okay? So we know here that m is positive. Okay? What does our steepness property show us? If I plot out a couple units here on my x-axis, okay, if I start at a particular point, okay, at this point, let's say x is equal to 1. If I move 1 unit to the right, in order to land back on the line, in this case, because m is positive, I have to move m units up. So I have to go up by a value of m, so whatever the slope is for this particular line, I go up by that many units, and then I land back at another point on the line. Okay. What happens if m is negative? Well, if m is negative, then let's sketch out another quick graph here. If m is negative, you'll find that the line falls as you go from left to right. So it will look something maybe like this. Okay, this line has negative slope. We don't know what the intercepts are. We don't really care what the line is. It's just a line with negative slope. So in this case, m is negative because it falls as you go from left to right. Again, let's plot out a couple units. Okay. If I start at a particular point on the line, okay, and I move 1 unit to the right, exactly like the steepness property says, in order to end up back on the line, I have to, in this case, move m units down. Okay, so I've moved m units down when I've moved 1 unit across in order to land back on my line here. Okay, so if m is positive, you move m units up to land back on the line. If m is negative, you move m units down. Okay, what happens if m is 0? If m is 0, if I move 1 unit across, I'm still on the line. Because when m is 0, okay, any line that has a slope of 0 is a horizontal line. It's one of those lines where y is equal to a constant, which would mean that I've got just this horizontal line. So again, if I start out with a particular point on my line, and I then decide to move 1 unit to the right, well, m is 0. So I don't have to move up or down. I'm still at another point on that line. Okay? So that's what the steepness property shows us. Let's do a quick example of this. I'm not going to do the whole thing here, but you can kind of see what the pattern is. So let's say we want to find 3 points on the line y is equal to 3 over 2 x plus 5 over 2 using the steepness property. Okay. As long as they don't specify what your starting point is, you can kind of pick whatever you like. I would tend to go with one of the intercepts as your first point. In particular, I would go with whatever the y-intercept is, because at the y-intercept, x is equal to 0. So then you can work your way along for x is equal to 0, x is equal to 1, x is equal to 2. But as I said, you can kind of start wherever you want and then use the steepness property. It's just an easier starting point if they don't specify, to start with whatever that y-intercept is. So at the y-intercept, we know that x is equal to 0. So if I plug x is equal to 0 into this equation, I get that y is equal to 5 over 2. We know that that is the case because this value is always the y-coordinate of that y-intercept. So I already know that the y-intercept is 0, 5 over 2. So hence that lies on the line. Now we can use our steepness property. So I want to know what the y-coordinate is when I've moved 1 unit over in the x direction. So when x is equal to 1, I need to find my y value. Now you could do this in several ways. You could plug x is equal to 1 in, which is actually equivalent to what we're doing if you think about it mathematically. But we'll use exactly what it says for the steepness property. So when x is equal to 1, so we've moved 1 unit over on the x-axis. We started at x is equal to 0. We've moved over 1 unit to x is equal to 1. I've then got to look at what my slope value is. For a start, my slope is positive. So I know I'm moving up by 3 over 2 units. My y value currently is 5 over 2. So from the steepness property, I start at y being 5 over 2, and I've got to move up by m units. I've got to move up by 3 over 2. So y would be my starting value of 5 over 2 plus my value for m. Okay, because m is positive, I move up by m units. If you add those together, they've got a common denominator, so we can add them easily. It's 8 over 2, and that is 4. So my next coordinate that I know is on the line is 1, 4. Let's do another one. Okay, so I'm currently at x is equal to 1. I'm going to move over to the right again by 1 point. So I'm going to move over to x is equal to 2. Okay, and again, I'm going to use my steepness property. So I'm currently at a y value of 4. Okay, and I'm going to bring in my steepness property. I am currently at a y value of 4. I'm going to move up by m units. So y would equal 4 plus my value for m, which would be, if you figure that out, that's 11 over 2. So my next coordinate would be 2, 11 over 2. Okay. You could just plug in x is 0, find the y-coordinate, x is 1, find the y-coordinate, x is 2, find the y-coordinate, and just plug them straight into the equation. That is literally what you are doing mathematically here. It's just putting it in a different way of wording it, basically. Next kind of example I want to do is, again, we're going to use the steepness property, and we are going to look at the line that has a particular slope and goes through a particular point. Okay, so find, I'm going to say we're going to find 3 points. Find 3 points on the line that has slope -2 and goes through, let's say 1, 3. Okay, and we're going to use our steepness property to do this. Okay, we're starting at 1, 3. Okay, so I know x is 1, y is 3. Using my steepness property, I'm going to move over by 1 point. Okay, so I'm moving over 1 unit in the x direction to x is equal to 2. So when x is 2, y is going to equal whatever my starting y value is, so whatever the y value is for my last point, plus what my value for m is, which is -2, which gives me 1. So the next point on the line is 2, 1. Carrying on, when x is equal to 3, y is going to equal whatever my last y coordinate was, which is 1, plus my value for m. Okay? Again, m is negative in this case, so I'm actually moving downwards. If you were to sketch this graph, you would see that actually occurring. So my next point is 3, -1. Okay? And then carrying on again, when y is equal to 4, when x is equal to 4, y is going to equal whatever my last y coordinate was, which is -1, plus whatever my value for m is. So I'm moving down by 2 units, which would give me y is -3. So my next point is 4, -3. Okay. So then you could plot those points out, join them up, and that would give you your sketch for your line. As we said before, this slope, all it is a measure for the steepness of the line, okay? The higher the magnitude of it, so whether it's a large positive number or a large negative number, the higher the magnitude of it, the steeper the slope. So if you have a very large positive number for your slope, that means you have a very steep line, but it's going to be positive slope, which means it's going to look like this kind of graph here. So it has a positive slope, but the higher that value for m gets, the steeper it's going to get, the more vertical it's going to get. If m is a very large negative number, you're going to end up with a line that still has this negative slope like this, but it's going to be very steep. It's just going to fall as you go from left to right rather than rise as you go from left to right, as it does if m is positive. So it's the same idea, it's just that these lines are going to get more and more like a vertical line the larger that value of m gets, whether it's a larger positive number or a larger negative number. Okay. If you have a slope that has a very small magnitude, so whether you've got a positive number that's closer to 0 or a negative number that's closer to 0, that line is going to get more and more and more horizontal. Okay, so it's going to go towards that horizontal direction, whether it be positive or negative, it's still going to look like it's getting more and more horizontal as it goes along, the smaller that value for m gets, whether it be positive or negative. The next type of form of a line that I want to look at is something called the point-slope equation of the line. So far we have looked at the slope-intercept form of a line. We've looked at the general equation for a line. Now I want to rearrange again, and this time I'm going to look at the point-slope equation of a line. It's still another equation for any particular line. It's just writing it in a slightly different form. The way that we write this particular equation is if we have a line that has a particular slope and goes through a specific point, then it's very easy to write down the equation of the line in this form. Okay, so that's when we use this, and then we can always rearrange it to be in one of the other forms of the line, but this is always a great starting point if you are given the slope and one particular point on that line. So if we are given a line that has slope m and goes through, say, x sub 1, y sub 1 is our particular point, okay? Then the equation of the line can be given by, okay, it's y minus y sub 1 is equal to m x minus x sub 1. Okay. As I said before, this is a great starting point if the two pieces of information that you are given are the slope and one particular point. You can then always rearrange it into either slope-intercept form or the general equation of a line. Absolutely up to you, and it also depends on what the question is asking. But this is always a great starting point if those are the two pieces of information that you are given. Okay. So let's go back to the previous example that we had, where we had a line that had slope -2 and it passed through 1, 3. Okay, that's exactly what we had here. We had a line that had slope of -2 and went through 1, 3. Okay, let's find the equation of that line. We found some other points that were on that line so that we could, if we wanted to, sketch out that line by plotting the points and joining them up. But let's actually find out what the equation of that line is. So we've got a line with slope -2 and passes through 1, 3. Okay, let's find the equation of that line. x1, y1 is this point here, 1, 3, and we know m is -2. So let's plug all of that in. Y minus y sub 1 is 3. So then I've got m is -2, x minus x sub 1 is 1. Okay. Now you can distribute out and you can rearrange this. I'm actually going to put this into slope-intercept form just because it's the form that we are most used to, especially when we are trying to graph things. So I'm going to leave my left-hand side the same at the moment, and I'm going to distribute out for my right-hand side. So I'm going to get -2x, and then -2 times -1 is +2. Remember, -2 has to multiply everything that is in those parentheses. Okay, people sometimes forget and only multiply it out into one of those terms, but it's got to multiply every term in those parentheses. Then we rearrange, and that's going to give you y is equal to -2x plus 5. So I've just added 3 to both sides, and that is my equation for the line. Okay. Another time that you can use this, and this is slightly more complicated, is if instead you are given two different points that lie on the line and you are asked to find the equation of the line. Okay. We can actually use this point slope equation of a line to then put it into some other form. And it's actually pretty easy to do. It's just that it looks very complicated at the start. So let's say I'm going to actually use the same example that we had, okay, to prove that this works. We're going to still use this example, but this time I'm going to pretend that we don't know the slope, but we are just given these 2 points that lie on the line. So let's say you had, in this particular question, find the equation of the line that goes through the points 1, 3 and 2, 1. That is all the information you have. You don't know the slope. You don't know any intercepts right now. You just know 2 particular points that lie on the line. Okay? And the question is, what is the equation of the line? Okay, we know the answer already. Okay, we just figured it out. Is y is equal to -2x plus 5. But how would we do it if instead we were given this information? Okay, well, if we go back, we were given an alternative definition for the slope, where if we had 2 separate points that lie on the line, we can easily find that slope m. Okay, if you remember, we also said that that was a particular equation to find the slope of a line given two different points that lie on that straight line. So that's all I'm going to use here. That will then give me my slope, and then I can use any one of these 2 points and go ahead and then find the equation of the line using that point slope equation. So first thing I would do is find the slope. Okay, that is always a good thing to find if you are not already given it. So I've been given 2 points on the line, I don't know a slope. So let's go ahead and find it. I'm going to say that x sub 1, y sub 1, I'm going to call that the first point that was given to me. And then x sub 2, y sub 2, it's going to be 2, 1. Again, you can put these the other way around. You would still get the same slope. It doesn't matter. You can try it out if you want. But either way, whichever way you label it, you will still get the same slope m. So if I plug this in, I'm going to get y2, which is 1, minus y1 is 3, over x2 is 2, minus x1 is 1, which gives me negative 2 over 1, which is just negative 2. So that agrees with what I actually had before, okay? My slope was negative 2. Now, I can go back to my slope-intercept form and plug in my value for m and either one of my 2 points. It really doesn't matter which point you use. You will actually end up with the same equation of the line. In order to prove this, we've actually already done it with the slope negative 2 and this point. To prove that you actually end up with the same equation regardless of which point on the line you use, I'm actually going to use this point and plug that into my point slope equation of the line in order to show you that we end up with that same equation. So I'm going to say I've got y minus my y coordinate, which here is 1, is equal to my slope x minus my x coordinate, which is 2. So I get y minus 1 is equal to negative 2x. Then negative 2 times negative 2 is positive 4. And then I add 1 to both sides, which gives me y is equal to negative 2x plus 5. So I still end up with my same equation. Okay. So to recap here, what have we done? We have done our first example where we have seen how to find the equation of the line if we are given a particular point on the line and the slope of the line. We can go ahead and find the equation of the line. I've put it into slope-intercept form just because that's the easiest form whenever you're trying to graph something and trying to visualize what it would look like. So it tends to be the go-to. So if you are given the slope and you are given a particular point on the line, you can go ahead and find the equation of the line. Also, if you are given 2 different points on the line but don't yet have the slope, you can still find the equation of the line by finding that slope m using that alternative definition for the slope, using those 2 points. We go ahead and find that slope, and then we can plug in that slope and one of our points into our point slope equation of a line and find the equation of the line that goes through those 2 points. The last thing that I want to go through in this section is something called the perpendicular property. Okay. Perpendicular means that 2 lines meet basically at a right angle. So it doesn't matter whether they are horizontal and vertical lines or whether they're actually diagonal lines when you look at them on a Cartesian coordinate plane. It doesn't really matter what the angle is, but it does matter that when you plot them out, that they're going to meet each other at right angles. Okay, that means that 2 lines are perpendicular to one another. So they could look like that, and then you could actually plot out, let's say, your x and y coordinate plane. Doesn't matter wherever it is, okay? So those 2 lines would be perpendicular to one another because they meet one another at a right angle. You can also see the x and the y axes, they are also perpendicular to one another. They meet one another at a right angle, okay? So 2 lines are perpendicular if their slopes are negative reciprocals of each other, okay? What does that mean? So let's write that out first, and then we will go through what that would mean in terms of a line having slope m. What would the slope be of the line that's perpendicular to it. So two lines are perpendicular if the slopes are negative reciprocals of one another. Okay. Same actually holds true the other way around. If you've got two lines and you find their slopes and the slopes are negative reciprocals of one another, it means that they're perpendicular. So this is actually an if and only if argument. It works both ways. So two lines are perpendicular means that their slopes are negative reciprocals of one another, and if two slopes are negative reciprocals of one another, it means that the two lines are perpendicular. It works both ways. Okay. What does it mean for negative reciprocal? Okay. If I go ahead and say that a line, we'll call it L, has slope M, it means that the line that is perpendicular to it, again, it works both ways, the line perpendicular to L has slope -1/m. Okay, so you do 1 divided by the slope that you are given for the line and then make it negative, and that will give you the slope of the line that's perpendicular to the original line. Okay, this only works if you have a situation like the black lines above. It actually doesn't work in terms of, like, if you were to look at like the X and Y axis, where one of those lines is vertical, because if you remember, a vertical line actually has an undefined slope. So it doesn't work if one of the lines is vertical and hence the other one would be horizontal. Okay, because obviously you can't do 1 divided by a 0 slope, that's undefined. So it doesn't work if one of the lines is vertical, because hence the other line would be horizontal if it was perpendicular to it. So this doesn't work out mathematically. But as long as your lines aren't vertical or horizontal, this does work. If you have parallel lines, okay, let's look at what parallel lines would look like. Again, I'm going to quickly plot out an X and Y Cartesian coordinate plane. Parallel lines have the same slope, okay? One's not steeper than the other. They both have the exact same slope, whether that be positive or negative. In this case, these lines would have positive slope because they rise as you go from left to right. But whenever you have parallel lines, they will always have the same slope. Okay, so if a particular line, one of these lines has slope M, then so will the other one. They both have the same slope. Okay. Let's do a couple examples to finish off. So we're going to find an equation of the line that is perpendicular to the line y is equal to -2x plus 5, and I'm going to put in the extra thing that it has to pass through the point 64. Okay. What does that mean? Okay. Well, I know that the slope of my original line is -2. So the line that is perpendicular to it the line that is perpendicular to this line has slope of negative 1 over negative 2. The negatives would cancel out, which would leave you with 1 over 2. So the slope of the line perpendicular to this line is 1/2. Okay, so we have the slope. What else do we know about this line that's perpendicular to y is equal to negative 2x plus 5? Well, we know it has slope 1/2. It also has to pass through this point 6, 4. This then turns into the exact same example that we had when we were looking at this point slope equation of a line. Okay, I have my slope and I have a point. I can go ahead and find the equation of the line. So I know that m is equal to 1/2, and I've got this particular point that lies on the line of 6, 4. So I'm going to use my point slope equation. And I'm going to say I've got y minus y sub 1, which is 4, is equal to m multiplied by x minus x sub 1, which is 6. So that's y minus 4 is equal to 1/2 x, and then 1/2 times negative 6 is negative 3. And then I'm going to add 4 to both sides, which gives me y is equal to 1/2 x plus 1. So this line here is perpendicular to this line here, and it has the added property that it passes through this particular point. Okay. Any line that has slope of 1/2 would be perpendicular to that original line that we were given. But we have added on that additional property that it has to pass through that particular point, and that gives us an exact equation. But any line that had slope 1/2 would be perpendicular to that initial line. We've just added in some extra stuff to find a particular line. Okay. Same deal again, but this time I'm going to look at a line that is parallel to that original line. So find an equation of a line that is parallel to y is equal to negative 2x plus 5 and passes through 6, 4. Okay, so we've found the line that is perpendicular to it that passes through that point. Now I want to find the line that is parallel to it that passes through that point. Okay. Well, my slope this time has to be the exact same slope of my original equation in order to be parallel to it. So I know m is negative 2. I again have the same deal as before, where I look at the point slope equation of the line because I now have the slope and I have a particular point. So I can plug this into my point slope equation of the line again. And I can rearrange. To give me this line. So this line is parallel to my original line and it passes through this point. Again, any line that you have that has slope of negative 2 would be parallel to your original line. But this particular line passes through 6, 4 as well as having slope of negative 2.